page 20, you can see here there's a diagram of the periodic table that gives you an idea of the valency, or the charges on ions, if you like, that would form from those groups. So our group 1 metals can only form single positively charged ions. Our group 2 metals, the alkaline earth metals, can only form 2 positively charged ions. The transition metals can all form 2 positively charged ions, but they can also form other ions. Our group 13 metal, so not everything in group 13 we would necessarily class as a metal, boron is metalloid, can form a 3 positively charged ion anyway. Then when we get to group 14, where carbon is, and we have some metals in here, they can form 2+ and 4+ ions. But up the top of group 14, our non-metals aren't really forming ions. Okay, that's carbon and silicon. Carbon definitely not really forming ions. Silicon is again classed as a metalloid. We don't really look too much at the chemistry of silicon. And then when we get across to groups 15, 16 and 17, the top of that is firmly non-metals, and they're forming negatively charged ions. And we don't really talk much about the chemistry of the metals that are lower down. What have we got? Lead, though, at the bottom of group 16. It can also form 2+ and 4+ ions, which is listed on your formula sheet. The table of common ions on the formula sheet are the ones that you need to be able to use. Okay? So you don't have to memorise this, but you do need to be able to find them on the formula sheet. And it's on that page there. So you've got common anions and common cations on page 4. But if we go back to thinking about, yep.
Just quickly, just out of interest, is there anything that's a 4- charge?
Not that I'm aware of, but I'd have to look up and see. There's no, I guess, not a limit as such. So there probably is, but not something that I know off the top of my head. What we need to use is this bonding model of these alternating positively and negatively charged ions to explain ionic bonding and the properties of compounds with ionic bonding. So remember how we had a cation and an anion, and we say that metals react by donating electrons, and so it makes sense that most of the time the cation is a metal ion. Okay, so mainly metal ions. And our non-metals tend to be on that side of the right-hand side of the periodic table, and they are accepting electrons, and so these tend to be non-metals. And also complex ions. We've talked about them having a high melting point because of that strong electrostatic force of attraction between the ions that needs a lot of energy to break it apart. We've talked about it conducting electricity, either in the molten or aqueous state, but not as a solid, because the cations and anions are fixed in that crystal lattice and they're not able to move. We need charged particles moving to have electricity being conducted. The next property that we need to think about for our ionic compounds is that they are hard but brittle. What does brittle mean? easily break. So if we're using this alternating charged sign in circles to represent our ions, if I hit this with a hammer, then what happens is that at some point, after a little bit of pressure has been applied, like charges line up. So if I'm going to break down there, what happens is if this moves down one, so if you can see, all I've done is I've shifted this column pair down one. Now like charges are lining up, and we know like charges repel, and so this means that then they will push apart. And so that means that with a little bit of applied force here, our ionic compound will smash. It will break apart. It's brittle. And another property is solubility. So a lot of them are soluble, and if you look on page 5 of your formula sheets, you will see that there's a table of solubility, and we'll figure out how to use that soon. But quite a lot of ionic compounds are soluble in water, and this is because of the Now when Amy was asking before about water conducting by itself, and I said it has a slight charge differential between the ends, that slight charge differential, we call that being polar. Okay, so because water is polar, it can actually break apart some ionic compounds. So if we think about one that we do know is soluble, like sodium chloride, then what happens is this is a representation of a lump of sodium chloride that I put into water. Then, so here's my water. Remember that the oxygen end of the water is slightly negatively charged. With the cation in the sodium chloride, the sodium ion, is more attracted to the oxygen in the water than it is to the chloride ions. And so the water is able to pull it off. And the same is going to happen with my negatively charged ion here, where the hydrogens are slightly positive. It's able to pull off the chloride ion because the sodium ions and the chloride ions are more attracted to the water than they are to each other. Okay, so the sodium ions and the chloride ions are more attracted to the water than they are to each other and therefore dissolve. And that means that they are soluble in water. So even though these are really strong bonds, electrostatic forces of attraction that we have to add a lot of energy to melt, for some of these ionic compounds, they are more attracted to water than they are to each other, and they will dissolve. So it's like, I don't know, being really thinking someone is really wonderful, you know, like you really like them to be your boyfriend/girlfriend or some sort of thing. And then someone else comes along and you think, oh, you know, in a moment they are no longer important to you. Your eyes are firmly focused over in this completely other direction. That's what happens to sodium chloride when it's dissolved in water. All of that attraction that it felt for the sodium ions and chloride ions means nothing now.
That's a great analogy.
So what we're saying is they're not faithful.
Totally unfaithful.
What's his comment?
Yeah. So there are a few faithful ions in the table there, the insoluble ones that stick out no matter how much water you throw at them. But there are others that just can't help themselves.
Well, so why did we say within water, oxygen is slightly negative? Why is that?
It's to do with a couple of features of the oxygen. Of how many valence electrons does oxygen have?
6.
6 valence electrons. So I can represent my water like that as well. I've got 2 unbonded pairs of electrons on the end of the oxygen. And to do with bond geometry that we do not cover in chemistry either, it's something that you'd have to do in uni, this is what pushes down those hydrogens, because by rights, oxygen should be a linear molecule, shouldn't it? Because our positively, the rule of thumb is that like repels. And we've got 2 hydrogens that really should want to be as far away from each other as they can. But they're pushed down by these unbonded electron pairs, and we end up with water is a bent molecule as well. And that's the technical term, okay? So it's bent, and the hydrogens are down closer to each other. So we've got if you like, an excess of electrons on that end of the oxygen, but not just that. If we look at where oxygen sits on the periodic table, right next to fluorine, it just needs 2 more electrons to gain that noble gas stability. And here they are with hydrogen, and hydrogen being quite willing to give away electrons, form the hydrogen ion, doesn't hang on to that electron very strongly. And so if we look at the oxygen's ability to attract electrons compared to hydrogens, oxygen's much stronger. So the electrons in this bond are actually closer to the oxygen than they are to the hydrogen in the bond, leaving the hydrogen a little bit positive, but the oxygen now surrounded by all these electrons, slightly negative. No net charge. Okay, we haven't talked about covalent bonding, we haven't talked about anything yet, but that's the reason why. Okay, and it's this incredible property of water that this is how life exists as well, because that's what we are. We're a bag of ions. And if we couldn't dissolve things, our nutrients, the oxygen, if we couldn't remove waste products, then we couldn't be alive like we are. So this is fundamental to life. Okay, and our last feature of ionic compounds is this they can keep on growing. We can grow huge crystals. As long as there are enough ions around to keep being added in, then it can get bigger and bigger and bigger. Okay, all we need is just more to slot in. And we'll stop there.